So, in this second part of the lecture, we're going to finally turn to the algorithmic aspects of predicate logic. So, in propositional logic, this was our main focus, especially the satisfiability problem. So, let's perhaps begin by looking at the satisfiability question for predicate logic. And we'll start straight away with a negative result due to Alan Turing, a very famous person nowadays, from 1936, and also proved independently, actually slightly earlier in the same year, by another famous logician called Alonzo Church. So this theorem it's Church and Turing independently in 1936. They proved that, unfortunately, there is no algorithm. So no algorithm exists. I mean, informally then, no computer program exists that performs the following task. So the input is a sentence. Phi in predicate logic, say of predicate logic. And the output is either yes if phi is satisfiable, and no if phi is not satisfiable. And the important thing about the algorithm that doesn't exist, the requirement is that the algorithm must always terminate with one of the answers, yes or no. As long as we give it a well-formed sentence in predicate logic, the algorithm would have to take whatever computation time it needs, but eventually, after some finite amount of time, it needs to give us one of the answers, and the correct answer, either yes or no, depending on what the sentence is. So the required algorithm needs to always return either yes or no in finite time. And there's nowadays in modern mathematical terminology, there's a succinct way. Succinct, that's a short way of saying that no such algorithm exists. The satisfiability problem for predicate logic has the property that's called undecidability. Is undecidable. So I won't write it down, but the notion of decidability, the actual definition of decidability, is now implicit in what I've written. So I am going to say this, and it is part of the course material. So a problem in which one gives inputs and one requires a yes/no answer, so that's inputs of a certain format, and one requires a yes/no answer according to whether the input belongs to one class or another, is said to be decidable, that's decidable, if there exists an algorithm that will always terminate in finite time with either yes or no, providing the correct answer. So if we have an algorithm that returns yes or no in finite time, a problem is called decidable. If not, as is the case with satisfiability, it is said to be undecidable. Let me just write, I'm not going to write the full definition, but just we'll just say that problems for which yes/no algorithms exist, ones that always terminate with the correct answer, algorithms exist, are said to be decidable. Okay, so rather a disappointing situation for satisfiability in predicate logic. From your point of view, the good side of it is that it means there won't be a second piece of homework of programming a satisfiability checker for predicate logic, because it would be rather unfair to set you such a task. Okay, so there's no problem that performs the satisfiability, that answers the satisfiability question, because satisfiability is reducible to validity by adding a negation and vice versa. A corollary is, and in fact this is the result that this is the result that Gödel and Church originally proved. Validity is also undecidable for predicate logic. So that is, once again, there is no algorithm that will input a sentence to in predicate logic, and it, in this case, for validity, will tell us yes if the sentence is valid and no if the sentence is invalid. Okay, but so what can we do algorithmically with predicate logic? Let's actually instead try to focus on positive things. So one thing we can do with predicate logic is we can get a computer to look at a proof that we write in natural deduction, say, and tell us whether it is a correct proof. So a proof is given as, in the style we've been doing it, as a list of formulas with a bit of additional annotation. And the point is, this list of formulas, each successive formula needs to either be an axiom or an assumption, or it needs to follow from previous formulas according to one of the rules of natural deduction. So we need to follow the rules. And a computer can look at our proof and tell us whether we correctly followed the rules. So that's not so surprising, because the rules are quite precise. Well, in fact, they're fully precise if you write them down very rigorously. And essentially, we've got a finite list of finite bits of syntax, and we just need to check that that finite list of formulas is constructed according to the rules that we have. So it's not so hard to see that one can write a program to check that a proof is correct. But that is a potentially useful thing, because in mathematics one can have very long proofs, and indeed mathematicians make mistakes. Sometimes because the proofs just get too fiddly and too complicated, and it's very easy for them to have a little oversight and not realise that they've made a mistake. And also in other areas, like for example software verification, which is an important motivation for the current course, one also wants to prove that programs behave in a way that's intended, and one way of doing that is to go through some formal steps of argument, so to give a formal proof using rules like the natural deduction rules in order to make the argument. And again, if that was left to just a human to do, it would be very easy to make a mistake, perhaps even easier than in a mathematical proof, because often programs are really awkward and complicated, and there isn't that much intuition to follow in trying to prove that they're correct. At any rate, it's a very useful thing to have a computer that will take as input a proof either in natural deduction or in some similar system, normally a bit more convenient for the user to write in the natural deduction, and the computer can make sure that the proof is constructed according to the rules for reasoning that one has. So in our case, the rules for natural deduction. So what we can say is that, we'll write this as a proposition. So this is a proposition. This is a positive result now. Proposition. There does exist an algorithm, or there do. That's not just one algorithm, so let's maybe say there do exist algorithms. That take as input a natural deduction proof. I'm just going to write an ND for natural deduction proof. And output yes, if it is a correct proof. That is, if it follows the rules, and no, if it is not a correct proof. Well, let's just say it's not. It's implicit that means not a correct proof. So actually in practice, one doesn't want to just see no, it is not a correct proof, but it's a bit like debugging a program. You don't want to just know that your program has a syntax error, you want to know what the syntax error and where it is. So in practice, a practical program based on this algorithm wouldn't just say, no, this is not a correct proof, but it would say you have an error of reasoning at this point, and then it would be up to you to correct it. Okay, so we can at least check a proof. So I'm not going to prove this as a mathematical proposition. The best way of thinking about it for yourself is how you would program such a thing. That's not totally impossible to think about, even from what we've done on the course. You just need to think about how you represent logical formulas using syntax. Well, we've already considered that for propositional logic, so you just need to deal with the more complicated syntax of predicate logic. How you would represent proofs, and how you would check that the proof follows the rules. I mean, it's quite a complicated thing to write. It would probably take 1,000 lines of code or something like that to, well, if you did it in the right language in the most efficient way, it would be less than that. But still, anyway, it would be some sort of reasonable amount of code to write this. But still, it's something feasible for you to think about. And the basic point is that once you've got the proof written down, at each stage there are only finitely many rules that can be applied. Well, in fact, one tends to annotate it with which rule has been applied, and the computer just needs to check that indeed the formula that's been written down does indeed follow using the rule in question. Okay, so we've got this nice positive proposition: a computer can check a proof. This is actually useful. So application. So it's not normally used just in predicate logic. It's used often in even more expressive or more convenient extensions of predicate logic. But the application is in something called computer-assisted proof assistance. So some famous ones of these are a system called Coq, Lean, Agda. Well, anyway, there are lots of others. But the idea is that these are computer applications that allow you to write proofs, and the computer checks that your proofs are correct, but actually the computer-assisted proof assistants do more than that. They also provide you lots of useful things for constructing, tools for constructing correct proofs. So it's a bit like an interactive programming environment in programming. So it doesn't just check your syntax, but it provides useful tools for actually constructing the program itself. It's pretty much the same thing with writing proofs using computer-assisted proof assistants. Okay, so that's one positive thing we can do. And based on that, the fact that we can check a given putative proof, that's something that looks like it should be a proof, and check to see that it's correct, we can get a nice theorem from that. So there is an algorithm that kind of decides validity of sentences in the following kind of way. So there is an algorithm that takes as input sentences, a sentence phi, and as output returns yes if phi is valid, but the difference with decidability is that in the case that phi is not valid, it doesn't return anything. It doesn't say no. But what it's doing is it is still trying to show that phi is valid. It never discovers that phi is not valid. So, but it runs forever if phi is not valid. So we get a positive answer out in the case that phi is logically valid. And in the case that phi is not valid, we sit around twiddling our thumbs, waiting for the computer to give us an answer, but we never get it. So eventually we probably give up. So, in other words, so that is, again, there's terminology for this. So the problem is not decidable. We've seen that validity is not decidable. There's no yes-no algorithm, but there is a yes algorithm that never tells us no, but at least tells us yes in the right cases. And this is halfway to being decidable, so it's called semi-decidable. So that is validity is semi-decidable for predicate logic. And the proof idea here well, it uses this fact that we can check a putative proof to see if it really is an actual proof. So we search through all, well, one way of looking at it is we search through all proofs that exist in predicate logic. In a systematic way. So that can be done because, as I keep on saying, proofs are finite lists of formulas, and formulas are finite strings of symbols, and proofs may have a little bit of annotation, but anyway, one can enumerate all potential proofs as like enumerating all lists of things that look like formulas, and then we can apply the proof checking algorithm we had in this proposition to check whether our thing that looks like a proof, that we're searching through a space of things that look like proofs, we can check that it actually is a proof. And eventually, if we do it systematically, if there is a proof of phi, eventually we will stumble across it. And then we can say, yes, phi is valid because we have a proof. Of course, this is terribly, terribly inefficient. There are more efficient ways to do it, which are to generate the proofs in an intelligent way, as far as possible. But however we do it, we will always be in the situation that we won't in general know how long it's going to take to find a proof, if there exists a proof. So we can never know, if we don't find a proof, if we haven't yet found a proof for phi, we can never know that there isn't a proof. We still need to keep on searching, and maybe there is one, maybe we just haven't found it yet. Anyway, at least we get some positive information out of this. So we have an algorithm that will try to find proofs and will then essentially give us some check on validity. And this again has applications. So the application here is theorem provers. So theorem provers are based on the above result. So what is a theorem prover? Well, essentially a theorem prover is computer application that you give it a sentence in predicate logic or some other logic that you're interested in, and it tells you whether it is valid. But often this is done in the context of, well, you have some axioms in predicate logic and you're really interested in, does the sentence you're looking at follow from the axioms? And that can be turned into a single theorem if you like, because you can have the theorem that you can have the sentence that the axioms imply the conclusion that you're looking for, or you can just think of it as a theorem prover allows you to have some axioms and to ask, does a particular sentence follow from the axioms? In any case, such things are implemented, and they have algorithms that are fundamentally based on searching through proofs, although obviously they work in the whole point is to get them to work in quite intelligent ways to try to find proofs. So this sort of technology has been being developed for a long time. It didn't really produce great results until I think the first major result was in the mid 1990s, when a theorem prover called Otter verified and solved an open mathematical question, which was, is every Robbins algebra a Boolean algebra? And it solved that question in the affirmative with quite a clever little proof that no human had been able to come up with. Since then, theorem provers have had other successes too, and the whole difficulty with theorem provers is that, as we know from mathematics, proving theorems seems to require quite a lot of intelligence. You need to concentrate rather hard and have a lot of insight into what you're doing. So it is the sort of area that is really ripe for exploitation by artificial intelligence, and now with the amazing advances in the last decade, in particular in artificial intelligence, theorem proving is becoming a very potentially important technology that's now under a lot of development. But anyway, the basic foundation of theorem provers is this theorem in predicate logic that validity is at least semi-decidable. So all theorem provers are going to be essentially constrained by this theorem, in that they will all enjoy the property that if they tell you, yes, your theorem is valid, then it means it really is valid and it has a proof, and in fact they will of course give you the proof. But if they run forever, or they come back and say, time out, I've been looking for 10 years for this proof and I still haven't found it, then you still have no idea whether the theorem is valid or not. There's a chance that the proof of it has just not yet been found, rather maybe quite a high chance. So, for example, it is not expected that current technology is getting near to the stage where one can put the axioms for set theory, which are the foundation of mathematics, into a theorem prover and put in the question, is the Riemann hypothesis valid? That's a famous open mathematical question, and expect to get an answer back. Or alternatively, maybe more relevant to this course, we could ask, is the equation P equals NP true? At the moment, nobody would expect a theorem prover to be able to answer that question. But at least we have this technology in development. It does have applications, particularly in the software industry, and it's fundamentally based on this theorem of semi-decidability of validity in predicate logic. So what about satisfiability? Well, satisfiability is not semi-decidable. We can't ask a theorem prover to say yes if a sentence is satisfiable, and maybe run forever if not. If we could actually, then validity would be decidable. There's a little argument for that I'm not going to go into. But anyway, that's how we know that, or that's one reason that we know that satisfiability is not semi-decidable. The negation of satisfiability is semi-decidable due to its relationship with validity. But satisfiability itself is not semi-decidable. The thing about satisfiability is you can get the no answer out, that something's not satisfiable, because you can find a proof of the negation, but you can't get the yes answer out. There is an algorithmic question closely related to satisfiability that is semi-decidable. And this is finite satisfiability, as it's called. So maybe we'll go to a new sheet for this. So finite satisfiability. And for finite satisfiability, the input is again a formula of predicate logic, or let's say a sentence. We can generalize to a formula, but and the output in this case is yes if there exists a finite structure. Finite structure such that and no otherwise. So a finite structure M means a structure whose underlying set is finite. And if the underlying set is finite, then we still have the interpretation of the predicate symbols as functions from powers of that set to truth values, and the interpretation of the function symbols as functions from powers of that set to the set itself. But because it's a finite set, all those functions are given by finite data structures. So the whole finite structure itself can be represented on a computer as a finite data structure. So again, we've got the negative proposition. Which is that finite satisfiability is undecidable. So there is no algorithm that always terminates and answers this yes-no question. Maybe it should really be a theorem. I don't have in my notes who this is due to. I've got a feeling it might be due to somebody called Trachtenbrot. But anyway, it doesn't really matter. But it's a relatively deep theorem, so it's not a triviality. But again, we're more interested in positive results. So it's a positive result. So again, call it a theorem. However, so the first one was a negative result because it says there does not exist an algorithm with certain properties, but the positive result says we do have an algorithm. So finite satisfiability is semi-decidable. So just like so again we have, this means we have an algorithm that takes a sentence as input and will tell us yes if there exists a finite structure that satisfies the sentence, and in the case that there is no finite structure that satisfies the sentence, will run forever. So the idea of the proof of this, so again we'll have a proof idea, is similar to the proof idea for validity, only this time we search models rather than searching proofs. And we can do that because we're only interested in finite models. So the proof idea is we systematically search through all finite structures M until we find one such that M satisfies phi, where phi is the input sentence. So the algorithm can systematically search through all finite structures because it starts with the structure with a one-element set, and well, you need to interpret the predicate and function symbols over that, but there are only finitely many ways of doing that, not very many in the case of the one-element set. So one checks whether phi is satisfied by any of those structures. Then you switch to the two-element set and you consider all different structures that can be defined over the two-element set. So that means all different ways of interpreting the predicates and function symbols over a two-element set. Again, there are finitely many. So you wait till you've exhaustively checked those. Then you move to three-element sets, and then four-element sets, and five-element sets, and so on. So you keep on incrementing the number of elements in the set by one. Each time you search through every single possible way of making a structure that has that many elements in it, and you go on forever. And if there is a finite structure that satisfies the sentence phi, eventually you will discover it. But it might take a very long time, because those of you who know some combinatorics will know that even simple kinds of structures like graphs, which are basically just sets with a binary relation on them, there's a huge combinatorial explosion on the number of, as you increase the number of elements in a graph, there's an enormous combinatorial explosion on how many graphs there are of a given size. So it's a very, very inefficient process, but at least in theory, this process will terminate eventually. You may have to be very, very patient, but it will terminate eventually if your sentence is finitely satisfiable. So that's the proof idea. There is one interesting part of this proof, which is checking that a formula phi is satisfied in a finite structure. So we're systematically searching through finite structures, and at each stage we want to check, is the formula phi or the sentence phi, is it satisfied in the finite structure? So let's put a box because it's the end of the proof idea. And so this process, this algorithm, involves checking for each structure M and sentence phi whether or not the structure satisfies the sentence. And this is called the model checking problem. Oops, I seem to have gone back a few pages. So the model checking problem. So the input is a formula phi, or a sentence phi, and the output, sorry, it's a sentence phi and a finite structure M. The output is yes if M satisfies phi and no otherwise. And we're going to end with the algorithm for doing this, for solving the model checking problem. And finally, we have a nice problem that is actually really feasible to do by an algorithm. It doesn't involve some searching for a very long period of time. So proposition, the model checking, I'm not going to say anything about the time now, but I will later. The model checking problem is decidable. So we really do have an algorithm that will answer yes or no as appropriate. So I'm going to end by describing the algorithm for the model checking problem. So importantly, the input is a sentence phi and a structure, because the structure is finite, as I've already said, that can be encoded as a finite data structure. You can think about that, but essentially you need to represent the underlying set and the interpretations of the predicates and function symbols. So we're going to give this algorithm that, or at least outline the algorithm that decides, does a given finite structure M satisfy a given sentence phi. But in order to get the algorithm to work, we need to basically recurse through the definition of the satisfiability relation that we gave earlier. And the satisfiability relation, we saw that in order to see whether a sentence was satisfiable, we needed to use the satisfiability relation more generally on formulas that are not sentences, that is formulas that have free variables. So also algorithmically, to write the algorithm, we're going to have to check actually satisfiability in a finite structure M of a formula phi that can have free variables. And because of that, we need to also not just have the structure and the formula around, but also have an environment around too. So because the satisfiability of a formula in a structure depends only on the free variables of the formula. We saw that at the beginning of the lecture. It's enough to just consider the environment working on the free variables. So we're going to do an algorithm for deciding, that is answering yes or no to, the relation that phi is satisfied by the structure M in environment rho, where let's start with M, where M is a finite structure phi is a formula and rho, let's put it down here, rho is an environment that is defined on the free variables of phi. So rho maps the set of free variables of phi onto the underlying set of the structure curly M. So we don't make rho a function on all variables because there are infinitely many functions on all variables, even uncountably many, for those who know about cardinalities. And because the definition of satisfiability of the satisfaction relation depends only on the free variables in the formula, this is enough. So here we've got a finite set of free, so of course a formula is a finite string of things, so a formula has only finitely many free variables in it, so we've got a finite data structure here which represents the function from the free variables to the finite set M. And this is by recursion. So the algorithm works by recursion on the structure of the formula phi. So we're going to say how the recursive algorithm is defined in different cases. And we look at all the different cases that we can have for the structure of the formula phi. So the case that phi is P, an atomic formula formed using a predicate symbol. Then we just check in the structure. We compute the interpretations of the terms, which are all elements of M. Of the structure curly M. We can do that because we've got a finite data structure representing the structure curly M, and using that we can go through the interpretation of terms. That bit's quite easy. I'll let you think about that for yourselves. And then we compute. Well, in fact, let's make it dynamic. So let's just add. So we compute then the result of applying the interpretation of the predicate to that. That's now, and we return yes if this is equal to t, to true, and no if it's equal to false. if we've got that phi is the equality, t1 equals t2, we compute the elements t1 according to row and t2 according to row. So these are both elements of M, and we return yes if equal, no otherwise. Let's do, say, implication. If phi is, let's say, phi 1 implies phi 2, we recursively compute we see if phi 1 holds under row and also if phi 2 holds under row, and we return yes if either this one says no, which means phi 1, so we're going to say if phi 1 is not true or phi 2 is true. So if the first recursive call returned no, and we return yes, or the second recursive call. Sorry, my writing's getting very messy now. The second recursive call returned yes, and we return no otherwise. And let's just do one more. So if phi is for all x phi prime, so phi is a universally quantified formula, and so it starts for all x, and phi prime is just the rest of the formula phi. Then we go into a for loop, which is for every a in M, we compute. So this is where we use the fact that the structure M is finite. There are only finitely many elements of the structure M. So we recursively, for every A and M, we recursively compute so I want to check that phi prime holds for every element A of the structure. So we recursively compute that in the structure M, we check that phi prime holds in the environment where we're not really updating x because row x wasn't free in the formula, so x didn't occur in the environment row. In this case, we're simply extending the environment with a value also for the variable x, because x is now potentially free in phi prime. So we extend this to the environment by adding the variable x and mapping it to A. So we recursively compute this, then so when the for loop has finished, we return yes, it is satisfiable, if every recursive call returned yes. Maybe one would make it nicer by saying itself returned yes. And the existential quantifier is very similar. Again, we recursively compute this value. So we go through all the elements of the structure, but this time we're trying to see if phi prime is true for at least one element A. So as above until, so let's maybe say the for loop as above. And then when loop has finished, we return yes if at least one of the recursive calls returned yes. And the way I've written it, we're going through every element, we're doing a for loop through every element in the underlying set M in both cases. You can make it more efficient by, in the universal case, as soon as you find a no, you can abort the for loop and say, yeah, of course the answer to the whole universal quantification is no because we found one element that fails it. And in the same way with the exists loop, you can abort as soon as you find a yes with the exists loop. Anyway, never mind about such fine tunings. One thing I want to observe about the algorithm is the amount of time it takes. So really, it's all done on simple recursive calls, breaking down the structure of the formula as you go, except in the case of quantifiers, where in the case of quantifiers, there's this extra for loop. And of course, that can be quite computationally expensive. If you've got a large structure, then the for loop is going to involve a lot of checks. So one can measure the amount of time the algorithm takes in the following way, which is the running time or the execution time or the time complexity. Let's use time complexity. Of the algorithm is going to use the big O notation. And it's big O of some measure of size of the structure, which is the cardinality of the set M, so the number of elements in the set M, to the power of D times the size of the formula, which is basically just the length of the formula as a string, where D is the quantifier depth, the so-called quantifier depth of the formula. So The quantifier depth is if you have a formula like for all x there exists a y such that for all z, and then some property holds without any quantifiers in, the quantifier depth there would be 3 because you have 3 quantifiers nested inside each other. Or for all x, for all y, for all z, for all w would be 4. And it's basically, if you write the syntax of the formula as a tree, as one often does with syntax, for those of you who know about this, it's basically the maximum number of formulas you need to go, sorry, not formulas, of quantifiers you need to go to reach the leaf of the tree. So I'm running out of space on this page. I don't think it's worth starting a new page. I want to make the following observation, is that often, so for example, in looking for finite satisfiability, we have one fixed formula, but we check the formula in many different models. And this is quite typical, that one has a formula and one wants to check it in many different models. You don't so often vary the formula as much as you vary the models. So we often fix a formula phi, but vary the models, or vary the structure. And in this case, we notice if we fix the formula phi, then we have a fixed size of the formula and also a fixed quantifier depth, because we have one formula and the maximum number of quantifiers we need to go to reach a leaf in the syntax tree is fixed. So in this case, the running time is polynomial in the size of the model. The exponent of the polynomial, the maximum exponent of the model of the polynomial, in fact the only one, is the number d, which is given by the formula. But that never varies. The size of the model can vary, but the formula doesn't. So in this case, model checking is polynomial time, polytime, or just polynomial, but is polytime, that's polynomial deterministic time bounded in the size of the structure M. So this is maybe the first efficient algorithm we have seen in this course, so we should celebrate that. As long as we fix the formula phi. And just, is there any space at the bottom? So this property is known, there's this property where you fix one parameter, the formula here, and vary the other, and as long as you fix the one parameter, your polynomial in the other is known as fixed parameter tractable. So i.e. tractable because it's polynomial time. This is polynomial time algorithms are thought of as being kind of efficient in a sense. So tractable means efficient. So i.e. model checking, we're really running out of space here. So i.e. model checking is fixed parameter tractable. This is not examinable what this means, just for those of you who are interested in this concept, where the formula is the fixed parameter and the model is the varying parameter. Notice if we allow the formula to vary, then the quantifier depth can will vary in general, and so the algorithm is in general exponential if we put both parameters, if we take both parameters into account. Okay, well, we've run out of space on this sheet of paper. I think we have also run out of time, so that's everything for this week. Next week we're going to continue with algorithmic aspects and once again move towards looking at a computer application that implements them. Anyway, that's everything for this week, so goodbye for this week.